So we are going to evaluate the residue of some functions at singular points. So when we discussed this in last class, we have seen a residue at an essential singular point can be evaluated by expanding the function into Lorentz series and picking the coefficient of 1 by z minus c. But if it is a pole of order m, you have this formula limit z tends to 1 by m minus 1 factorial limit z tends to a, m minus 1th derivative of z minus 1, z minus a the whole raised to m into f of z. So we make use of both of these to find the residue at the specified singular points of some given functions. The first function we see is find residue at z is equal to 0 of z into cos 1 by z. So here you can see z is equal to 0 is a singular point of 1 by z, and hence it is a singular point of this function, or this function is not differentiable at z is equal to 0. And if you differentiate, if you expand cos as a series, you can see that this will be z is equal to 0 will be an essential singular point. So in this case, we just write the series expansion of this function. So we can write f of z is equal to z cos 1 by z, and expanding cos 1 by z in series, you get 1 minus 1 by z the whole square by 2 factorial plus 1 by z the whole raised to 4 by 4 factorial, etc. And multiplying with the z in the z outside the bracket, we get z minus 1 by 2z plus 1 by 4 factorial z cube, etc. So this is the Lorentz series expansion of this function about z is equal to 0. And from here, you get residue of f of z at z is equal to 0 equal to, we are writing the coefficient of 1 by z, which is equal to minus 1 by 2. So at essential singular points, you write the series and pick the coefficient of 1 by z minus c to get the residue. Next function, find residue at z is equal to 0 of, the function is 1 plus e raised to z divided by sin z plus z cos z. So obviously 0 is not a 0 of the numerator. Numerator z ന് പകരം 0 കൊടുത്താൽ നമുക്ക് 1 ആണ് കിട്ടുന്നത്. പക്ഷെ ഡിനോമിനേറ്ററിൽ z ന് പകരം 0 കൊടുത്തു കഴിഞ്ഞാൽ നമുക്ക് 0 ആണ് കിട്ടുന്നത്. ഇനി ഇത് എത്ര പ്രാവശ്യം അല്ലെങ്കിൽ ആ 0ന്റെ ഓർഡർ കാണാനായിട്ട് നമ്മൾ ജസ്റ്റ് ഈ ഫംഗ്ഷൻ എടുത്തിട്ട് ഒന്ന് ഡിഫറൻഷിയേറ്റ് ചെയ്ത് നോക്കുക. സോ g of z is equal to sin z plus z cos z എന്ന് കൊടുത്തു. Then obviously g of 0 is 0. Then g dash z is equal to cos z plus cos z minus z sin z. So g dash 0 is equal to 2. That means first order derivative is non-zero. So z is equal to 0 is a 0 of order 1. ഒറ്റ പ്രാവശ്യം അത് 0 ആയിട്ട് അപ്പിയർ ചെയ്യുള്ളൂ. അപ്പോൾ ഡിനോമിനേറ്ററിൽ ഒരു പ്രാവശ്യം ന്യൂമറേറ്ററിന്റെ 0 അല്ല. So you can conclude that z is equal to 0 is a simple pole. Okay, so if it is a simple pole, our formula to get residue is residue of f of z at 0 equal to limit z tends to 0 z into f of z, z minus a into f of z. So limit z tends to 0, z into f of z is 1 plus e raised to z divided by sin z plus z cos z. And to get the limit, you can just adjust the terms. So taking that z to the denominator, this function can be written as 1 plus e raised to z divided by sin z by z, right? Taking this z to the denominator. And in the second term, z cancels and we get cos z. And as z tends to 0, 1 plus e raised to z tends to 2. And sin z by z, we know as z tends to 0 tends to 1. And cos 0 is also 1. So we get the residue as 1. So second question പ്രത്യേകത ഇതാണ്. ഇങ്ങനെ ഒരു ഫംഗ്ഷൻ തന്നു കഴിഞ്ഞാൽ ആ സിംഗുലർ പോയിന്റിന്റെ അല്ലെങ്കിൽ പോളിന്റെ ഓർഡർ എത്രയാണെന്ന് കാണാൻ വേണ്ടിയിട്ട് എത്ര പ്രാവശ്യം ന്യൂമറേറ്ററിൽ 0 ആയിട്ട് അപ്പിയർ ചെയ്യുന്നുണ്ട് അതിന്റെ ഡെറിവേറ്റീവ് കൊടുത്ത് നോക്കിയാൽ മതി. നോൺ സീറോ ഡെറിവേറ്റീവ് വരുന്നതിന്റെ തൊട്ട് മുമ്പത്തെ, അതായത് ഫസ്റ്റ് ഓർഡർ ഡെറിവേറ്റീവ് ആണ് നോൺ സീറോ വരുന്നതെന്ന് വെച്ച് കഴിഞ്ഞാൽ ആദ്യമായിട്ട് z is equal to 0 is a 0 of order 1. ഇനി സെക്കൻഡ് ഓർഡർ ഡെറിവേറ്റീവ് ആണ് എടുക്കുമ്പോഴാണ് നോൺ സീറോ കിട്ടണമെന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇറ്റ്സ് എ 0 of order 2 and so on. അപ്പൊ അത് ചെക്ക് ചെയ്യാം. അതിനനുസരിച്ച് ഇവിടെ നമുക്ക് അത്രയും പ്രാവശ്യം ഡിഫറൻഷിയേറ്റ് ചെയ്താൽ മതി. ഇപ്പൊ സിമ്പിൾ പോൾ ആയതുകൊണ്ട് നമുക്ക് ഇവിടെ ഡിഫറൻഷിയേറ്റ് ചെയ്യേണ്ട കാര്യമില്ല. we use the formula limit z tends to 0 z into f of z. Okay. Now next function. Determine singular points and residue at each singular point. So the first function is f of z is equal to z square divided by z minus 1 into z minus 2 the whole square. So obviously the singular points are z is equal to 1 of order 1. It's not a 0 of the numerator. And z is equal to 2 of order 2. എല്ലാം poles ആണ്. So pole of order 1, pole of order 2. So we use the formula to evaluate the residue. So residue of f of z at 1 equal to, being a simple pole, you can write limit z tends to 1, z minus 1 into f of z, which is equal to limit z tends to 1, z minus 1 into z square by z minus 1 into z minus 2 the whole square. So z minus 1 cancels, and giving z the value 1, we get 1 by 1 equal to 1. Now when you come to the other singular point, its order is 2. So the formula changes. We should write this is 1 by 2 minus 1 factorial. Limit z tends to 2. This 2 stands for the order of the pole. The order is 2. So 2 minus 1 factorial. This 2 stands for the singular point 2. Limit z tends to a. So limit z tends to 2. d raised to 2 minus 1 by dz raised to 2 minus 1 z minus 2 the whole square into f of z. So we get limit z tends to 2, 2 minus 1 factorial is 1, and the first order derivative of z minus 2 the whole square f of z is z square by z minus 1 into z minus 2 the whole square. So here the term z minus 2 whole square cancels, and you differentiate this one time. Just find the first order derivative. Limit z tends to 2, z minus 1 into 2z minus z square divided by z minus 1 whole square. And I am not going to simplify this expression. I am just going to give z the value 2, and we get 1 into 2, right? Minus z square is 1 divided by 2 minus 1, 1 square. So again the residue is 1. So it is pole of order 2, that is the only difference. So multiply with z minus 2 the whole square, differentiate once and give the limit as z tends to 2. Now the next function we consider is no difference. It's a fourth order polynomial, fourth degree polynomial, that's all. So factorize ചെയ്യുമ്പോൾ 4 roots വരും. We can factorize this as z square minus 1 into z square plus 1. And this can still be factorized into z minus 1 into z plus 1 into z plus I into z minus I. So we have 4 singular points and each of them is a simple pole. So the singular points are poles of order 1. They are z is equal to 1, minus 1, I and minus I. And being simple poles, the evaluation of residue was quite simple. We can write a residue of f of z at 1 equal to limit z tends to 1, z minus 1 into f of z. So it will be easy for you if you write the factorized forms and cancel the terms. You can write this as limit z tends to 1, z minus 1 into, we have factorized this into z minus 1 into z plus 1, and my aim is just to cancel the z minus 1. So you may keep the other term as it is, z square plus 1. So I can cancel the z minus 1, give z the value 1, you get 1 by 2 into 2, which is equal to 1 by 4. Similarly, you can do with the other singular points. And let us do one more question. So f of z is equal to, I just want to emphasize the order of the singular point. 1 minus e raised to z divided by z raised to 4. So obviously z is equal to 0 is the only singular point, and while thinking of its order, we check whether z is equal to 0 is a 0 of the numerator. Obviously, giving z the value 0, we get 1 minus 1, which is equal to 0. So if you take g of z is equal to 1 minus e raised to z, നമ്മൾ നേരത്തെ ചെക്ക് ചെയ്ത പോലെ തന്നെ g of 0 0 ആണ്, and g dash z is equal to minus e raised to z. G dash 0 is not equal to 0. So z is equal to 0 is a 0 of order 1 of numerator. And if you look at the denominator, z is equal to 0 is a 0 of order 4. Right? Z raised to 4 ആണ് കിടക്കുന്നത് of denominator. So if you combine these two, you can see that, you can see that z is equal to 0 is a pole of order 3. It appears once in the numerator, 4 times in the denominator, so that the order of the pole is 4 minus 1, which is equal to 3. And hence you can find the residue of f of z at 0 as limit z tends to 0. This should be 1 by 3 minus 1 factorial, limit z tends to 0, d raised to 3 minus 1, so d square by dz square of z minus 1 the whole cube, z minus 0 the whole cube into f of z. So we get 1 by 2 factorial, which is 1 by 2, limit z tends to 0, d square by dz square of z cube into f of z, that is 1 minus e raised to z divided by z. Now you can differentiate this and apply the limit. While we take the first order derivative, we get limit z tends to 0, z into minus e raised to z minus 1 minus e raised to z divided by z square. So what we have is minus 1 plus e raised to z minus z e raised to z divided by z square, and we have to differentiate this one more time, then apply the limit. So we have 1 by 2 limit z tends to 0, z square into the derivative is e raised to z minus e raised to z, by right, minus z e raised to z, this divided by, minus 1 plus e raised to z minus z e raised to z into 2z, denominator into derivative of the numerator, and these two terms comes from the product rule applying on this fact on this term. So this divided by z raised to 4. Okay, so cancel the terms that you can cancel. Nothing wrong with this expansion. I can cancel z square e raised to minus z. Why should I go for all these expansions, right? It's a simple function, 1 minus e raised to z divided by z. Z raised to 4. It will be quite easy if you write the Lorentz series, because this is a simple function. And you can write this as 1 plus z square by 2 factorial plus z cube by 3 factorial, etc. This divided by z raised to 4. 1 and 1 cancels, and we get the series as minus z by z raised to 4, that is minus 1 by z cube, then minus z square by 2 factorial, so minus 1 by 2 factorial z square, then our important term minus z cube by z raised to 4, so minus 1 by 3 factorial z, etc. And I just need this term to write the residue. Obviously, you can see what I have said before, that is z is equal to 0 is a 0 of order 3. The Lorentz series extend up to 1 by z cube, and looking at this expression, I'm sorry, I cancel all these things. ഇങ്ങനെ പോയാൽ നിങ്ങൾക്ക് ആൻസർ കിട്ടും കേട്ടോ, പക്ഷേ ഈ ഫംഗ്ഷൻ സിമ്പിൾ ആയതുകൊണ്ട് ഇതിനേക്കാളും എളുപ്പം സീരീസ് എഴുതിയിട്ട് ചെയ്യാനായിരിക്കും. അപ്പോൾ ഇതിൽ നമ്മൾ ചെയ്യുമ്പോൾ നമുക്ക് കിട്ടുന്നത് റെസിഡ്യൂ of f of z at 0 equal to minus 1 by 3 factorial. അപ്പോൾ ഇവിടെ ചെയ്യുമ്പോൾ നിങ്ങൾ ചിലപ്പോൾ z ക്യാൻസൽ ചെയ്ത് പോവും, പിന്നെ 0 by 0 ഫോമിലേക്ക് വരുമ്പോൾ ലിമിറ്റ് കണ്ടുപിടിക്കാനായിട്ട് എൽ ഹോസ്പിറ്റൽസ് റൂളൊക്കെ അപ്ലൈ ചെയ്തിട്ട് ചെയ്യേണ്ടി വരും. ഓക്കെ, അപ്പം അതുകൊണ്ട് വേണം ഇത് കുറച്ചും കൂടെ ടൈം കൺസ്യൂമിംഗ് ആണ്. മെത്തേഡ് തെറ്റാണെന്നല്ല, ഇറ്റ് ഇസ് time consuming than this. So the series being so simple, you can expand the series and pick the coefficient of 1 by z to get the residue at z is equal to 0. And when you expand the series, you can see it is not a pole of order 4, it's a pole of order 3.